Okay, so yesterday we left off with this. We were talking about structure of the atom. So I'll kind of quickly go back and just review the stuff we talked about. We talked about how the idea of the atom was actually first devised by a Greek thinker. What was his name? Democritus, right, okay? But it was rejected because everybody liked the idea of everything being made of 4 elements because it made more sense at the time, okay? Then, 2,000 years later, people are doing experiments that are finding that the behavior of matter says that there might be something to this tiny particles idea. So John Dalton comes up with the atomic theory and his 4 points, okay? The first one being Democritus' idea that all matter is made of tiny indivisible particles called atoms. Okay, that atoms of the same element are identical, and atoms of different elements are different. Atoms can combine with one another in simple whole number ratios to form compounds. And in a chemical reaction, atoms can be separated, joined, or rearranged, but not changed into atoms of other elements. Okay, so those are the 4 points. Make sure you know them for next week. Then we talked about how the next question for Dalton was, what do atoms look like? And he said, I don't know, they're really small, so maybe they're like a sphere. And everyone's like, good, that works for us, okay? And it worked for a while. And then J.J. Thomson comes along, he's doing experiments that involve reactions that produce charged particles that can flow through a wire or electrical current. The solid sphere model doesn't explain where those charged particles come from. So we modify the model of the atom. Becomes the plum pudding model, which is still a solid sphere, but now it's got these tiny negatively charged particles loosely embedded on the surface that can come off in a reaction and produce an electric current. Then things get crazy for a while. We discover protons, we discover neutrons. Nobody knows what the atom looks like anymore. Nobody can prove one way or another what it looks like until who comes along and runs this gold foil experiment? Rutherford. Okay, so Rutherford comes along and he runs that experiment with the really thin piece of gold foil. He shoots the neutrons at it, and he finds that lots of the neutrons get through, but many of them are deflected because they actually strike the nuclei of the atoms in the gold foil, okay, proving that an atom does have a very small, dense nucleus, and that the electrons must be surrounding the nucleus in some way. That's kind of where we left off. From there, the argument became very quickly, what are the electrons doing? Where are electrons? How do they move? Do they move? Do they stay put? Why don't they fall into the nucleus? They're negative. The nucleus is positive. Why don't they just attract each other? Okay, things like that. So people needed to kind of study and figure out what are electrons doing. Okay, everyone was fine with the idea of the nucleus, but now there was the matter of how does it work? Okay, so lots of studies went on. People knew that electrons could actually be separated from an atom. Protons can't be separated from an atom. Neutrons can't be separated from an atom because they're bound together in the nucleus. But electrons are not. Okay? And in reactions, electrons move around. J.J. Thomson discovered that in his experiments. So they knew electrons couldn't be part of the nucleus. Okay? So people started kind of devising ideas about where will these electrons be, and how do they, for the most part, stay with their atom, but sometimes leave their atom, right? And what they kind of theorized was that they must orbit, okay? They knew at that point that the Earth revolved around the sun, the moon revolved around the Earth, and that was due to an attractive force between them, gravity, okay? So maybe electrons did something similar. Electrons, after all, were negative, and the nucleus of the atom was positive, and that would create an attractive force that could lead to an orbital pattern. Okay? Now that was kind of a simplistic idea, but people accepted it because there was no way to prove or disprove that idea. So, welcome to the boring world of Niels Bohr, okay? The person who first devised what happens with electrons, or what they do. And he came up with what's known as either the Bohr model or the planetary model, okay, of the atom, saying that basically electrons have fixed orbits that circle the nucleus. Okay? Now, it's not like our solar system's orbits. There are some orbits that contain more than one electron. Okay? Do electrons ever run into each other? No, they don't. Okay, it's not like planets, because planets, they could attract each other, right? Because they have mass and gravity could pull them together. You wouldn't want two planets sharing an orbit around the sun, that'd be bad, okay? But electrons won't run into each other because they're all what? They're all negative. So if they get too close to each other, they naturally repel each other, okay? So in this first orbital, or orbital shell, okay, there could be up to 2 electrons, okay, depending on the atom. Basically every atom except hydrogen would have 2 in it, okay? So that would be the smallest one. And then the next one out could hold 8, and the next one out 8, and so on and so on. And you just get more and more shells as an atom gets bigger, okay? People accepted that because, again, there wasn't anything around to prove or disprove that electrons did that. And of course, ones that are near the outside might be the ones that would be lost in a chemical reaction when electrons get traded, okay? All made sense. People were generally pretty good with that. Okay? The problem is that while this might be what an atom looks like if I was to take a picture of it and freeze it in time, electrons don't stay put. Okay? At the time, people didn't know that. Okay? But as they did more experiments and studies of kind of natural processes in the world, they discovered that some things could only be explained by electrons being able to move further from or closer to the nucleus of the atom, okay? And that's what we know happens now. In fact, it's how photosynthesis works, okay? When plants capture energy from the sun, the electrons that are part of the chlorophyll molecule gain energy from the sun, kind of like how a solar panel works, okay? The electrons gain energy and they get excited and they move really, really fast. The spot that they're in can only contain an electron that has X amount of energy. Once that electron gets more energy than that, it'll take what's called a quantum leap, and it will jump from that lower energy level to a higher energy level, okay? And it'll keep doing that until it's at an energy level that can contain it. That's what happens during the day when the sun is shining on the leaves of a plant. When it gets dark, when the sun goes behind a cloud, there's nothing to hold those electrons out there anymore, and they naturally fall back towards the nucleus. When they fall back, they give off the energy they had gained as they jumped away. That's the energy that's used to turn carbon dioxide and water into sugar. Okay? It's also a similar process. If you've ever had like a shirt or a watch that has like some pieces that glow in the dark, you know, like you put it in the sun and then you take it into the dark and it glows for a little while. Okay? Same process. Fluorescence works that way. Okay? The electrons gain energy, they get excited, they jump to a higher energy level, and then when you move them into an area that can't sustain them there, they fall back down and they give that energy off as light, and they glow for a short period of time. Okay? Bohr's model couldn't explain that, because his model said, these electrons belong here, and they stay here, and they just go around and around, and they're happy. Okay? Except that's not really what they do. Okay, so that leads us to our currently accepted model of the atom, de Broglie's electron cloud model. Okay, it seems a little random at first glance, okay, because it's called the cloud, and we've just pictured electrons everywhere randomly, but they're actually not. There are actually regions, kind of like Bohr predicted, within that cloud where electrons are more likely to be. Okay? They can move anywhere within those regions, and they can jump from one region to another as they gain energy. All right? So that's how de Broglie's model explained that thing that Bohr's couldn't, which is why we currently accept that. Okay? So de Broglie, okay, and his electron cloud model is now what we currently accept to be what an atom actually looks like. Okay, one of the things you're going to be asked to do in this course is you're going to be asked to draw a picture of an atom. Okay, spoiler alert, I'm telling you right now, one of the questions on your unit exam for chemistry is draw a picture of X. Okay, I just pick an element off the periodic table, you've got to draw it. Okay, in that drawing I'm going to want the following things. The right model, that would be this one. Okay, and the right number of protons, neutrons, and electrons for that particular element. Okay? Do we want to go through an example? Yes is the right answer. Okay. So let's say I ask you to draw me a picture of, let's say, sodium. All right? So if I ask you to draw a picture of sodium, okay, well, rather than draw a big circle, how many protons does sodium have? 11. Okay? The atomic number, okay, this number right here, is the number of protons in the nucleus of that atom. Okay? What's this number?
How much the entire atom weighs?
Right, this is the atomic mass. Okay? This is essentially the sum of the protons, the neutrons, and the electrons, which are so small they basically make up no part of this. Okay? So, I've got 11 protons. How many neutrons do I have? 12. Okay? The number of neutrons doesn't always have to equal the number of protons. The way we figure out the number of neutrons, and you might want to write this down. Okay? We'll just write number of protons equals the atomic number. And no, that's not hashtag protons, that stands for number. Okay? E first. Okay, if we want to calculate the number of neutrons, we take the atomic mass and we subtract the atomic number. Okay? Remember, the atomic mass is the sum of the mass of the protons, the neutrons, and the electrons. And as I said, the electrons are so small that they basically make up no part of that number. Okay? So if we subtract those two numbers, we'll get the number of neutrons. So for sodium, if we do that, it's going to be 22.99 minus 11, which leaves me with, can I have 0.99 neutrons? So how many do I have? 12. Okay, and it's always going to work out that way. Okay, you're never going to get, well, I shouldn't say never, you're rarely going to get a whole number when you do this. You're going to have to round up. Okay, it's never going to be confusing. It's never going to come out to like 12.3, and then you're going to go, which way do I go from here? You're not going to have to worry about that. Okay, it always works out to something that you could obviously say is, I need to make that bigger, or I need to make that smaller. Okay. All right, because you can't obviously have fractions of a neutron. Okay, everyone okay with that? All right, how many electrons does sodium have? 11. Okay, the number of protons and the number of neutrons is always the same, because an atom has to be electrically neutral. And it has the same number of protons or positive charges as it has negative charges. All right, so now that we know that, now we can draw a picture of what sodium looks like. Okay, so what I would do is I would draw a nucleus that contains what two particles? Protons and neutrons. Okay, so I got to draw 11 protons. Okay, what needs to go in all the spaces I left? Yeah, how many? 12. Right. Okay, there's my nucleus. The right particles are in it, in the right numbers. Where do the electrons go? What does de Broglie say surrounds the nucleus? just like data, they're in the cloud. Okay? And literally, you can draw it like this. Done. Okay? That would be a 5-mark question. Okay? You'd get 1 mark for having the electron cloud model, hence write the word cloud in there. Okay? You'd get 1 mark, okay, for having the protons, neutrons, and electrons in the right places in that model. And then you would get 1 mark each for having the right number of protons, the right number of neutrons, the right number of electrons. Okay? 5-mark question. Pretty easy 5-mark question? I kid you not, I'm putting that on there. Okay? Okay, so make sure you've got this written down here. Oh, we didn't write the number of electrons. Okay. Okay, also here's the atomic number. Okay, questions on that? So, the number of protons can't change because we can't change the nucleus of an atom by any physical or chemical means. Okay? We can with nuclear means, okay, by shooting particles at it and trying to break it apart. Okay? But that doesn't generally work unless you already have a fairly large and unstable atom. Okay? That's why we don't use sodium in a nuclear fission reactor. Okay? What do we use in a nuclear fission reactor? What's the fuel for a nuclear power plant?
Hydrogen?
That would be for a fusion system.
Uranium?
Uranium, yeah. Okay. Now, specifically certain isotopes of uranium, okay, uranium-238, okay, is a very popular one. Sometimes we use plutonium. It depends on what type of nuclear power plant you have. Okay, plutonium is often produced in nuclear power plants as well. Okay, so we use those really, really big atoms. Right, an atom of sodium only has 11 protons, 12 neutrons, 11 electrons. Okay, if you look at uranium, it has 92 protons in its nucleus. And then 238 minus 92, we're looking at 140 something. Anyway, okay, neutrons. So it's big. It's really big. And the more neutrons you get in the nucleus of an atom, the less stable it is. Okay? Because neutrons don't have a charge, and protons like to be attracted to something and hold them together, and so those kind of atoms tend to be less stable, which is why they're also radioactive. Okay? Less stable atoms are going to break down on their own, decay radioactively, giving off radiation in the form of free neutrons that come flying off. Okay? So that's kind of how that works. Does that sort of make sense? Okay? But remember, it's neutrons that are coming off. Okay? Not protons. Okay? And the reason that's important is because the properties of an element are caused by the number of protons that it has in its nucleus. Okay? So hydrogen is a simple gas because it has 1 proton. Okay? Sodium is a metal because it has 11 protons. Okay? A metal that reacts violently with water. Okay? Magnesium is the way it is because it has 12 protons in this nucleus. Each element has a different number of protons, and that determines their physical and chemical properties. Okay? Everybody all right with that idea? Okay? That's an important thing to remember as well. Okay? So, structure of the atom as we understand it, there's a dense, positively charged nucleus that contains the neutrons and protons. There's a large volume of space surrounding the nucleus in which electrons can be found. So, in fact, atoms are made up of a lot of empty space. That's what Rutherford's experiment proved. Okay, so if we're simplifying what the cloud area kind of looks like, okay, this is kind of it. Okay, there's different orbitals. Okay, an orbital is a region around or within the cloud where electrons are more likely to be based on their energy. Okay, I kind of said that before, but this is kind of what some of those look like. Okay, so your simplest orbital would be this 1s. I'm never going to ask you that number. Okay, I'm just kind of illustrating here. This would be the lowest energy orbital that electrons could be found in. Okay, then you get the 2s orbital, which is also just a sphere, okay, but it's bigger, right? Electrons would have to have gained energy to go from this to that. Okay, now this orbital can only contain so many electrons, this one can only contain so many electrons. Okay, they get more energy, they can go to the 2p orbitals, there's a 3s orbital, there's a whole bunch of other weirdly shaped orbitals that go around them. There's one that's shaped like a donut that goes around the middle that's not on this diagram. Okay, there's all these different regions that electrons can be found based on how many electrons the atom has and how much energy those electrons have. Okay, you'll learn more about that like day 2 of Chemistry 12. Okay, so all atoms are made of protons, neutrons, and electrons. Okay, how can the atoms of one element differ from another, as Dalton said in his atomic theory? Okay, the answer is that all elements have different numbers of protons in their nucleus. Okay, so it is the different numbers of subatomic particles, okay, protons in particular, that influence the properties of the different elements. Okay, so make sure you got that. There's usually multiple choice stuff kind of around that. Right? That was kind of one of the arguments that chemists had during all of this time was, if all atoms are made of the same things, why aren't all atoms the same? Okay? If everything's made of protons, neutrons, and electrons, how can everything be different? Okay? And what they found was they're different because they have different numbers of these same things. Okay? So if you want kind of an analogy, the number of protons is to properties of an element as DNA is to the different characteristics people have from each other. Okay, so what makes you unique, the number of protons, is what makes one element different from another. Okay. All right, questions there? Ready good with that? Okay. All right, in your workbook, your digital workbook here. The first page of that chemistry digital workbook has some questions on it, okay, that have to do with the lesson we just went over. Okay, and I would like you guys working on those right now. So if you open up this one here, that's that one that says Unit 1 Chemistry Worksheet Package. These are the questions I would like you working on, okay? The atomic theory questions. I will give you the remainder of today's period to work on those, okay? And probably a little bit of time on Tuesday, okay, to finish them up. We'll go over them on Tuesday in class, and then we'll move on to naming ionic and molecular compounds on Tuesday. Okay, so do your best to answer those with complete sentences. Okay, and I mean, you're not necessarily going to find the exact answer for each of these questions. You're going to have to come up with some stuff, do some reasoning, okay, given what you know, to give kind of full answers for some of these. Okay, these are not coming in for marks or anything like that. Okay, I'm just going to go over them in class. Okay, but you'll